This is a video presentation for Intro to Feedback Control Systems at Colorado School of Mines. I am Mark Gilliland. We also have Eugene on and Carlos Diaz working on this project.
Prime has a radical idea of delivering packages rapidly using drones. They call this their Amazon Prime Air. With this, of course, comes challenges, one of them being descent. Initially, a descent alone when using a drone would be straightforward, but Amazon Prime Air will be dealing with packages of various dimensions and weights. To have an effective package delivery drone, certain criteria will be met for the system. This will be overshoot to reduce chance of collisions during height oscillations, settling time so that the drone can deliver the package rapidly, and recovery from disturbances such as wind and other outside interference.
To model the plant of our system, the quadcopter itself, we used simple physics concepts. We selected the mass of our drone and payload to be 10 kilograms. This was founded on the prototype Amazon drones, and you can find a citation in the report. We selected the damping ratio to be non-zero, but still much smaller than the mass, so that the system behaved significantly underdamped, just like the real world. For our system, we selected force as an input, and the height, or just position on the y-axis, is the output. Our system is unstable, as a unit step input results in a unbounded output approaching infinity at infinite time. Our transfer function for our plant, the open loop system, is shown here as 1 over ms squared plus bs. By using a mass of 10 kilograms and a damping ratio of 0.1 newton seconds per meter, we can find our final transfer function as 1 over 10s squared plus 0.1 s. As you can see here, the step response for our system looks very similar to figure 4 in the example document. To analyze our system, we can first look at the step response. The step response can be shown to be not bibostable on its own, because given a bounded input, unit step, we see an unbounded output, parabola. By inspection of our open loop transfer function, we can see that we have a single integrator. Therefore, the response to a unit step will result in an unbounded response, as the integral of the unit step would be a unit ramp. We determined that our plant was very likely to be disturbed by an outside source. We selected wind for our main disturbance, as this makes the most sense for a quadcopter. Wind can be modeled as a unit step, unit impulse, or unit ramp. To make our project interesting and the most robust, we selected unit ramp. The plant itself is required to follow basically only a unit step, or perhaps a ramp up to a certain point. Any unbounded inputs wouldn't make much sense for a quadcopter, so we did not need to worry about these as inputs.
For the initial design of our system, the following criteria were chosen. Through transient response design, we chose an ideal 0% overshoot. This accounted for height oscillations that needed to be dampened in order to reduce risk for collisions while descending. We chose a settling time of less than 20 seconds. In the interest of time and efficiency, these drones would need to drop off packages relatively quickly. And then for our steady state behavior, we decided that the system would need to reject impulse, step, and ramp responses for disturbances. This would be akin to, say, as a burst of wind, steady wind, and increasing wind, respectively. And our system would look something like so.
Next, we derived the transfer function for this system.
And we took the Ruth Hurwitz stability test of this and found our K values. And for our initial PI controller design, the K values need to be that the KP would need to be greater than negative 0.1, and that the Ki would be greater than 0.
Our preliminary design choice for the controller was a PI system, which had both a integrator component and a proportional component to the controller. Based upon this, we got the disturbance rejection shown here, which disturbance from a ramp input results in a finite but constant error. The ramp input cannot be completely rejected with just a simple PI system. Another integrator or different control approach would be required. However, it is beneficial that the ramp input is still finite. To verify that other design options were possible, we analyzed a PD controller that uses both a proportional and derivative component. We found that this was better at mitigating overshoot, which the PI controller was not, but was unable to track a ramp disturbance. Lastly, we implemented a PID controller, which was the best of both worlds. We are able to eliminate oscillations and minimize the overshoot to about 25%, but overshoot was still present. We are able to minimize the ramp disturbance to 10% of the final output, or 0.1, but are not able to eliminate it based upon the controller architecture. To determine our robustness of our system, we used gain margin and phase margin. This accounts for perhaps improperly modeled dynamics or a poorly built controller. We determined the gain margin to be infinite because we see that the phase approaches negative 90 degrees and negative 180 degrees is required to have a finite gain margin. Our phase margin was determined by the intersection, and that approximates to about 107 degrees phase margin to the negative 180. It can also be shown with a Nyquist plot. As you can see, no matter how much we amplify it, this will never approach negative 10 right here, and so our gain margin is infinite. But if we rotate the plot around enough, we can. So that's approximately 107 degrees. We verified this with the MATLAB SISO tool as well. Here's the original step response to our original system. To verify that the gain margin was indeed infinite, we used a multitude of gains for the system. So a gain of 10 looks something like this, which, while it does have a slightly different step response in this area, still approaches our value of 1 at infinity. It does not go unstable to an infinite response. At a gain of 10,000, we see almost an identical graph.
So in conclusion, we chose a PID controller to implement the system that we modeled. It allowed for us to have a very limited overshoot as well as negate disturbance. However, when we ran the finalized tests, we found that our transient response time was still greater than 20 seconds, which was not what we wanted to achieve. However, we did find that the overshoot and disturbance were mutually exclusive, so we could only choose one or the other, and we figured that it'd be best to have both of those addressed and then just have a longer response time, because in the end, for practical purposes, one would want to have their package delivered intact rather than have it delivered fast but broken. So our group recommends utilizing the PID with the parameters set for overshoot and disturbance rejection. In our verification phase, we chose a PI controller. However, that showed that it could not address all the issues that we had and thus proved inefficient. In the end, we had this PI controller address 2 of the 3 issues, which we find to be sufficient enough for in terms of delivering a package safely to the customer without damaging it. However, we were willing to accept the fact that it could not address the transient response time.
It is also important to note that our transient response time, we were evaluating with the step response and with the settling time. And the settling time at 20 seconds, it was only 1.5% above the target input, and so that's very, very close. It's not as if it was off by 10%. So depending on your definition of settling time, it may have been an acceptable parameter.